Good morning, good afternoon, and thanks for joining us at Smartlogic's webinar, Machine Learning Myths versus Reality, How to Use Semantics to Get Trustworthy AI Outcomes. Our speaker today, we're excited actually to have our speaker today. He's the president and CEO here at Smartlogic. And before I turn the presentation over to Jeremy, I have a few housekeeping items. First of all, this webinar is being recorded, and all of you are in broadcast mode. If you have a question, and we encourage questions, please put them in the question section of the GoToWebinar panel, which you'll see on the right-hand side of your screen. And finally, this broadcast is being recorded, and replay information will be sent to all registrants following the broadcast. And with that, I'm going to turn it over to you, Jeremy.
Well, thank you, and thank you for everyone for joining. This is, I think, the second of a series of webinars we've been doing around interesting subjects concerning semantics. The basic purpose of this webinar is to illustrate how semantic technology, which is itself a lot of AI in the form of natural language processing and text mining, and both of those use supervised machine learning, how they augment other upstream and downstream AI engines, such as robotic process automation, OCR, chatbots, deep learning, cognitive computing. And I suppose the way of introducing semantics into this is that semantics assists these other AI engines by providing the ground truth, which is basically the Rumsfeldian known knowns that you have in the form of metadata. And that this metadata, when it's properly synthesized and referenced, reduces the complexity of the maths and boosts data veracity because you're not having to machine learn stuff you already know. And I go to the next question, I suppose, is why is this important? Well, it's because most AI algorithms can be boiled down, and I know that this is a simple simplification for any maths grads in the room, but basically you can boil it down to multidimensional polynomial regression mathematics. And the more multidimensional the mathematics in machine learning, the noisier the result. And the simpler we can make it, the more trustworthy the result and the best chance of delivering business value. So that was the basic purpose of the webinar. But what I wanted to do was show you how semantic AI, which is what Smartlogic specializes in, it's a new technology, how we approach the classification of data, the harmonizing of data, the extracting and enriching of data to make other AI projects business worthy. And I say business worthy because so far there's a science experiment that's been going on in many R&D departments of organizations, but actually does the business trust the output? And we'll come to some of those issues, and we'll look at it by going through some of the myths of what machine learning is and what it isn't and what it's good for and how we can make it better. So we really want to talk about how semantics boosts data veracity, veracity meaning truthfulness, trust, quality of data. I'm going to attempt to take you through a look at the polynomial regression mathematics, but I'm not going to do it by looking at formulas or even that. We're going to do it with pictures and games on this webinar, because I think it's important if we're considering what is this machine learning, we need to understand the algorithm, well, not the algorithms, but the process of getting the algorithms to work. We also need to gain an understanding of the role of training sets, because they're one way to ground the algorithms. And there is another way, and we'll come to that, but it is, of course, a semantic way. It's the creation of the appending of metadata to the data, and we can compare and contrast the two methods. And then we'll go through how AI gains the added value of semantic-driven data veracity. Our customers call these 10-10 projects, 10% of the cost and 10% of the time than a traditional old way of working type data project. So AI, what is real? Well, artificial intelligence, the promise, I think we can all agree, is compelling. The promise, very simplistically, is the ability to automate higher order work functions using digital rather than human labor at a fraction of the cost, and also get improved results. So there are certain fields where the digital labor is better than the human labor at consistency, and we'll come to that. I mean, interestingly, McKinsey's, they're saying that the adoption of currently demonstrated automation techniques could affect 50% of the world economy, 1.2 billion employees, 14.6 trillion in wages. We're not going to address the interesting subjects of whether robots should have to pay income tax in this webinar. We're going to talk about slightly more down to earth, how you get your AI to work. But it's an interesting concept. And Gartner was saying that by 2020, 30%, a third of all the CIOs will have included AI in their top 5 investment priorities. But it's delivering on the promise, that promise to automate higher order work functions with better quality, requires organizations to work with high fidelity, high veracity data, because data is the underlying asset of every AI application. And it goes without saying that analyzing a mess gives you nothing more than an analyzed mess. We know this from all the work we've been doing, not us, but as IT professionals over the years. It's been said in other ways, garbage in, garbage out. But here we're now analyzing a mess and trying to get machines to learn, and how if they learn over a mess, then they will get a learnt mess. So the AI that Smartlogic can talk about is a subset of quite a large field, but it is the area that we are well regarded for. We feature in a number of Gartner Magic Quadrants, including the metadata management. We're a leader in that. And we can talk about machine learning, which is what the main process of this webinar is about, and natural language processing, which then takes into account classification, content extraction, unsupervised and supervised learning methods. So, if you were to meet me at a dinner party and I was on my favorite subject, which is Smartlogic, I would probably not talk about expert systems or vision or speech or planning or robotics, and but I am we're very good and specialists at the bit that's highlighted in grey. And of course, being a semantic software company, we can't start a conversation without some good definitions. And the first definition, of course, is I quite often get, well, Jeremy, what is this semantics? Well, it's a noun, and it is actually the branch of linguistics, which is the study of language, which is concerned with meaning and is the capture and communication of concepts and the relationships between those concepts. Now, if we think a little deeper about, well, what is a concept? A concept is a word or phrase used so an idea can be conceived in the mind of either oneself or in the mind of another. It's a way of transmitting and receiving ideas. And if you think about business, concepts are used to communicate an idea of how something is, which we would say was real world, or how something should be, which is best practice. So you've both got, best practice, this is how we should do something, as a concept, and you've got the concept of this is how something actually is. And of course, as business, we communicate using concepts. There are a few here on the screen, but we know what profit is, or we know what EBITDA is, or we know what an FTE is. We know that we might be FATCA compliant, which is a compliance for American tax to go through when you're opening a bank account. We understand the concept of top secret, or maybe a SKU number, or a late payment, or a research report, or an executive team. So these are not just strings of letters, which is what we're referring to at the bottom. These are things, and these things are captured in concepts. And the way we connect them is with a relationship between two, is with the relationship, which is also a noun, because all organizations run on relationships between concepts. So, for example, the concept of profit is up due to lower fixed costs. We're joining two concepts together in a relationship, and that communicates something about that organization. We could say that Jane Jones is promoted to SVP, or the inventory of SKU number such and such is 42. So the point I want to say, get across, is that concepts plus their relationships is the meaning. And what Semantic AI is doing is putting concepts and relationships together in the meaning using software. So we're doing it using machines. Quite often it's called things, not strings. So strings is how search engines work. They go and they look at, letters, but they have no idea of what that thing is. They just know that it's a string of letters. And what we're talking about here is providing the semantics, the meaning behind the data. So there is an old way of working. We're very used to it. I call it the siloed enterprise. And if we look at what actually is happening, you've got many different audiences using many different systems and applications, all the way from now customer and business and AI analytics, business applications, robotic process automation systems, websites, portals, chatbots. And that level of systems application is connected with hardwired meanings and relationships which are predefined into the data formats in the application code. And it's done at design time. And that means that when something changes, humans have to get involved. And it's not business humans, it's usually technical humans who have to get involved. Because offline, if we have a change of relationship or meaning, then the parties have to define, communicate between them the knowledge needed to make the change. And then they recode the data structures and the program logic to accommodate that change. And then apply these changes to the database and the application. And only then can we actually implement the change. So that's why, in many ways, the cost of making changes to one's information systems and one's systems applications is high to make a change, because there are all these individual hardwired connections between systems applications and the information services. The semantic enterprise offers a new way in that you're putting in place a layer, an abstraction layer, which is above the information services and below the systems applications, that allows all of those systems to reference the meanings, the concepts, and the relationships in one place. And what that does is it gives one place to go for all the different applications for the meaning and the data. So that all the data, whatever silo it's in, can become an addressable enterprise data in context to the data request. And very specifically within machine learning analytics or business and customer analytics, we find that the ability to harmonize and enrich meanings and concepts in one place benefits every system, all the systems applications and all the information services, because they're all accessing, if you like, the known knowns. So I want to start with an exercise in dimensions and myths. So we're moving, because at Smartlogic we use a lot of AI in our software, and we have our NLP stack, which is a whole branch of AI in its own right, as you saw. And in text mining, we use machine learning, and because we know its limitations. And we know how semantic technology, which is a combination of machine learning and more deterministic, or, if you like, more procedural algorithms, it can eliminate these limitations. So this next is an exercise where I want to start to introduce a few myths. So this is we're on a virtual meeting. We're in a virtual meeting room here on this webinar. So this is my view. If it's coming through, yep. This is my view of our webinar. we have a lot of people on the webinar today, and this is how I see it. And to do this first exercise, I want to start with a bit of a play exercise using all of us here in this virtual room. Right? We will act both as the data and the machine, because I think, after all, we have got many different implicit data attributes as us, and we have an excellent machine processing unit inside our heads. And when you consider that the role of AI is to provide insight through better analytics or improve efficiency by automating more mundane tasks, then as supervisors of these new digital workers, we need to understand the processes that the machine worker must go through to be believable and trustworthy. And then the fun is, what better way than walking through that process ourselves? And very quickly, we're going to expose some myths around AI and machine learning. And in the latter part of this experiment, I'm going to show you how we bust these myths. So don't worry, no one's going to be put on the spot for any personal views, but we are just going to go about organizing our data in this virtual room into categories and see if we can discover insights, or at least understand how difficult data trustworthiness or veracity is to achieving with using mathematics alone. Remember, the mathematics is the so-called, the algorithm that learns. And the first myth I want to bust is you just give the machine the data, it learns, and then delivers useful insight. So exercise 1 is to imagine you're in this conference room, and to imagine looking around the room. And now if you could write down how you would categorize and sort into logical piles and what insight you gain. You've got implicit data associated with yourselves, and you've got a machine processing unit in your heads. So take 30 seconds, look at this screen, and work out how you would sort this room. It's actually quite difficult, isn't it? I bet someone was asking, you were asking yourselves, how should I sort this room? The type of roof, is that what you meant? Did you mean the lighting? Did you mean the size or the number of the seats or the color of the seats? They may have made it onto some of your lists. I also hazard that gender, age, hair color may have made it onto others. Actually, I think probably gender, age, hair color might have made it onto many, which goes to indicate quite a nice side of natural bias, because as we're humans, we will jump to the conclusion that people in the room are the most important objects, right? But equally, shoe color, handedness, whether you're left or right-handed, whether the person's wearing glasses, would have been equally acceptable fact sets for analyzing this room. What this does is illustrate that without context for both the question you are answering and the data you are analyzing, we don't get very far. And context is important. Context, in the sense of machine learning, is delivered by training sets and here is another thing, high veracity metadata. So when we look, and we're going to look a little later at training sets in this webinar, but you can't just give the machine the data and it can't just learn and then deliver useful insight. You have to have the context for the question you're trying to answer and context over the data that you're analyzing. And right now, and the machine learning algorithms, which is maths, gets that context from training sets or metadata. and usually a combination of the two. Now, metadata is interesting stuff. Most of us think of it as technical. You know, the date that the file was uploaded to the content management system, maybe the security marker. But actually, metadata, if you in its widest form, is the various facets of an information asset in order to improve its usability through its life cycle. And it goes far beyond just those technical facets. It is used as a reference for business-oriented and technical projects, and it builds the foundations for describing, inventorying, and understanding data for multiple use cases, and specifically analytics. So when we're looking at machine learning analytics and AI in general, you know, metadata has a massive part to play, and we will show you where its role is in a little while. The second subject I wanted to go through is machine learning and training sets. And what are they? I mean, very simplistically, machine learning is the construction of mathematical algorithms, so maths, statistics, and we've mentioned the polynomial theorems that we use, that can learn from and make predictions on data. And they work by building a mathematical model, which I will refer to as a construct, from input data. So you give it data, you've got some maths, you have if you like, a construct of mathematics to look at the data. And in order to give it context, the training set is carefully compiled to set the machine. Right? We then have to validate that using a validation set. We have to use that as a control to compare the output. So we give the thing a training set once we've set the machine, which involves quite a lot of mathematics and some fiddling around with parameters and some tweaking of knobs. We then have to go and validate that the way we've set the machine is right to compare the output. And when we've done that, we have to have a new test set, which is a new set of data that's been unused in training to test the machine on new data to see how good it is. So when people say training sets, what are they? Aren't they easy to assemble? No, they are not. They are very difficult to assemble because actually it's not just a training set. It's training sets, a training, a validation, and a test set for every data dimension that you're trying to look at. And we'll look at that in a minute. But just because it says we'll get together training sets, actually it's quite hard work. And one of the ways that semantics helps is to reduce the reliance on training sets. If we go into a bit more detail on training sets, the construct, which is the algorithm, they call it, is fitted from a training data set. And the construct is trained, it's called supervised learning, and it produces a result which is then compared with the target. Okay. So then, based on the result of the comparison, the parameters of the constructs are adjusted. And when you're happy with that, we can call it a stage one machine. The output from that stage one construct is then compared against the validation data set. And the validation data set provides a known control. If the machine passes that known control, we'll call it a stage two machine. And the test data set, which is using data that's never been seen before by the machine, we have to assemble that as well. And that gives a measure of its accuracy in real life. And if we're not happy with the accuracy, we have to rinse and repeat that process until we get to a satisfactory accuracy. Now, this all it's simple, it's logical, but actually it's complicated in the sense that getting the data sets together is important. We don't want data sets with test sets with training sets with bias in them. We don't want to introduce bias. And so we move on to the second set of myth, the second myth I want to talk about. The second myth is we will quickly assemble the training set, then we will pour it into the machine, and it will deliver actionable intelligence. Well, actually, as we've seen, this is a lot of effort, time, and requires specialist skills. Getting these sets together is time-consuming, and it's intellectually difficult. And the more data dimensions needed for the analytics task, the harder the set gathering and the assembly gets, because every data dimension needs 3 training sets before you can put it to work. And we'll talk about what do we mean by a data dimension in a minute, but basically it's a data type. It's a lot of time, effort, and requires these specialist skills. Guess what? Those specialist skills are not the business. Let's say we're doing we're machine learning over some marketing data. Well, guess what? Marketing experts are not always good data scientists. In fact, quite the opposite. It's the maths grads who are setting the algorithms, right, using the training sets, but it's the business that is the knowledge holder of what that data is. So by using machine learning without semantics, we are disintermediating the business experts from the construct creation. And if we do that, we find that business doesn't trust the output because the output probably has not been fully understood during the testing. Okay, and the maths grad who's been doing, or the maths grads, because that's why data scientists cost such a fortune, is a very specialist skill. And we really want to have a way of getting the business connected to the data so that we can be sure that our machines are being accurate. So I wanted to have another exercise. Hopefully that you enjoyed the first one, which was looking around the room. But I wanted to, and this is my exploration of polynomial multidimensional mathematics using pictures. But I wanted you to think of us as now the trained machines in this room. And we'll take the easiest case. How would you split the room based on the color of the shirts being worn today? I want white and black in one grouping and all other colors in the other classification. And that's easy, right? It's easy, isn't it? Because we, as trained machines, we understand the concept of color and we understand the concept of shirt. First thing you would do to organize this room in black and white on one side and colors on the other of the shirts is that anyone not wearing a shirt needs to leave the room, and then everyone wearing a shirt goes into one of 2 groups. And you go to one side or the other side of the room. And of course, that's easy to see. It's a one-dimensional classification. We've got black and white on one side, and we've got colors on the other. But if you stop and think about it, the concept of shirt is relatively easy, but it does require some semantic intervention, as you might really be referring to your shirt as a blouse or a top. And does it or does it not include turtlenecks? And moving on to the concept of color, black and white is easy-ish, but could involve calibration for the types of gray. But what if it was all purples on one side and reds on the other? And then maybe you can see how noisy it becomes without good definition of what purple is, what red is, and when purple becomes red. So we humans, we take these concepts easily. Learning machines must be trained, and they need guidance, they need definition, they actually need authoritative specifics, which leads nicely onto the concept of authoritative metadata, something that semantics provides. Let's say we want to classify the purples, and it's no longer a straight line. In fact, because it's red, blue, and shirts, it's more dimensional. It's a 2-dimensional classification. And we start to see the simplicity of a single line, one-dimensional classification turns into a more complex shape to get just the purples in the room. And that shape is a two-dimensional shape. And so drawing that shape in maths is much harder. And that's basically what the algorithms are trying to do, is to sort out the data into different piles in different ways. And they use multi-dimensional statistical models to do it. And the more data types, the more dimensions. It's quite difficult to see dimensions on a flat screen, and actually it's hard for us to get beyond the fourth dimension in our minds because, of course, you've got X, Y, Z and time. But actually we've had customers who've had hundreds of thousands of dimensions in their machine learning algorithms, and it gets very, very noisy. And noise means reduction in quality, and reduction in quality means it's not trustworthy. So how do we reduce the noise? The maths grads who I've been talking about, who I've got a huge amount of regard for because they're brilliant at doing this sort of stuff, getting dimensional classification to go, actually call it the curse of dimensionality. As we add more data types, and then let's say in this case on the left I've added in hairstyle, because we're sitting in this room still, virtually. So let's add some data types. Let's say hairstyle, we can see that. And let's say shoe size, because that's a bit more hidden. And the reason why we've added this is because the business, and remember business asks for interesting things, in our world, this three-dimensional model is being put together because analytically the business wants to know the relationship between coloured shirted humans with short hair and how this relates to size 7 shoes or smaller. It's no longer a simple line or even a two-dimensional, but it's a complex shape. So that's a reasonably easy shape, but now you can start to see why the dimensions just keep on coming. And as we build up these dimensions, and as we add data types, the maths dimensionality of the maths goes up, and this generates more and more noise. Right? So how do we need to reduce the noise, we need to up the quality. I'm going to change track a little bit, and I want to talk a little bit about the third myth. And we'll come and put this all back together in a short while. So the third myth, specifically for business, is that machines are going to be autonomous decision makers soon. AI is not mature enough to provide full autonomous decision support. I think we know that. And at Smartlogic, we think the A should actually stand for either assisted or augmented, and there is a chart coming up, but it's definitely not artificial. We believe it can automate the next level of repetitive work, which is compelling from a cost and efficiency perspective. And there's a data quality yield as well, because actually if you're getting machines to do the work, tend not to go out to lunch, tend not to get tired, tend not to get bored. And it's the consistent application of digital processes gets you accurate and traceable outcomes. So we can see all of that. But the idea of autonomous decision makers soon is not here. Yes, in a very focused, you come back to the idea of the dimensionality, if we can keep the focus tight, such as a car can drive itself, it's got a nice tight focus, but don't rely on the car driving you in the snow and the sleet, because actually the road signs have gone, it's lost some of its data types. We can see that we're good at using AI and machine learning in natural language processing. We can equip it with a tight focus of the grammar of the language. But when you think about business with all its variances, we believe the A should stand for assisted or augmented intelligence. And it really is the interplay between human and machine, with the human providing the knowledge transfer and the control, and that makes the difference between actionable business insight or it's just a maths experiment being done by maths grads in the research department. I thought this might be useful, this picture, because it shows the continuum. There's this thing called autonomous decision, which is actually which is also in AI world sometimes known as, the singularity, the point at which machines become fully autonomous. That's clearly a way away. But equally, we've been automating repetitive tasks, including manual and cognitive aspects, basically in the last decade. And in the next decade to come, I think we'll be doing assisted and augmented intelligence, where it's helping the business value chain, but the machines are not dynamically adapting to changes in information, or that's the assisted side. Or if it's augmented, the algorithms are adapting to changing data, but they're not automatically making decisions, but they do put humans in the best position to do so. And Smartlogic's playing with its product Semaphore in this assisted to augmented spot, because that's where we see the most business value for our customers. And I now want to turn to basically bringing this all back together and show how the machine learning process can be dramatically reduce the dimensionality using quality metadata. So what do we mean by metadata? And if we're calling it assisted intelligence, I'm not going to try and change the world's view and get rid of the word artificial. I've given up with that. But if we think about what assistance is needed, well, we need to reduce the number of dimensions in the algorithms. Why? Well, so the math is not so noisy and quality outcomes are achieved. We need to authoritatively mark up the data with definitions and standards. Why? So the algorithms don't spend unnecessary compute cycles figuring out if a person is an employee or a contractor, when this is a known piece of data, or if a name is a known brand, and the list goes on. So in this picture, we've got our shirts, we got the color purple, we can type it. This is metadata that we can append to the data type, which are the known knowns. Our shoes, we've got the size 8, and it's a brogue. But we've also got the ability to assemble much richer knowledge models that we can add to and augment, if you like, the labels on the shirt with a whole load of extra stuff that we already know about it coming out of our data systems and our knowledge models. So, for example, one tag of purple in the knowledge model will tell us that it's also an RGB 5050-145, that the die number is 54255F, that the blouse, which is typed, is a shirt, it's the same as a shirt, that it's 767677 model number, and it only comes in our brand, which we happen to call Happy, right? So by combining data and the knowledge model, we can endow this data element with a huge amount of ground knowledge, like ground level data, known knowns about this piece of data. And we can carry on with the size 8 brogue, and we happen to know that it's only size 8s are manufactured in France, and we know that the designer was called Acme Design, and we know that and with the hairstyle, it's a bob. But actually it's also difficulty 4, and that requires an experienced cutter, and they have to have a salon training certificate B+. So you can see how the knowledge model, which is the reference point of all the concepts, can join with the actual data that's appended to these things to create a really solid view. So in fact, what you end up with, and we're going to add a couple more data dimensions in the next slide, just come. What we're suggesting is that machine learning can be used on the unknowns. In this case, I've added 2 extra data types. I've added hat styles and trouser styles on the right. But when you know stuff, the contextual knowns with metadata and the references to the knowledge models allows us to machine learn on the unknowns, so it keeps the dimensionally down, but we've got quality data about the knowns. So we're not using our compute cycles to find out stuff we already know. We're using semantics to label the stuff about what we know about it already, so that we don't have to go through. We can reduce the dimensionality very rapidly because we're not having to get large cloud servers machine learning and trying to figure out whether a brand is a brand or is it just the name of a person, because we know that stuff already. So as I come up to my 45 minutes, which is how long I was asked to speak for, I just wanted to summarize. We've taken hopefully an enjoyable, interesting journey. You've given me 45 minutes of your time, and maybe you'll give me 15 minutes of some questions, for which I thank you very much. But hopefully it's been useful in the sense that you now understand a little bit, hopefully in a nice way, of the dimensionality behind machine learning and the algorithms. We see that the subject matter expertise is paramount to deliver context. We believe that humans provide that context and that meaning through knowledge, and that knowledge can be modeled. We know that meaning is referenced from knowledge models and it's encoded in metadata. And we see this assisted augmented intelligence is a very nice business value add for one's operations, but it is an interplay between human and machine. And if one's going to spend time putting together training sets, let's at least put together the training sets on the stuff we don't know about, to get the mathematical algorithms to hopefully find new insight. And let's be smart and use semantics and metadata to properly harmonize and tag up the data that we do know about it. Even if they're sitting in siloed systems, we can bring them up into a layer, provide a nice common place to access it. And that way, we'll get our AI projects to be successful, because we've reduced the dimensionality of the mathematics, and we've also harmonized and enriched the data with our knowledge so that it is fully addressable, actionable data. Thank you very much.
Thank you, Jeremy. And thank you, everyone, for your time. I have a few logistical questions, which I'll deal with, and then I have a couple questions for Jeremy. First of all, for those of you who are wondering, yes, this webinar is being recorded, and anyone who's registered and attended or not attended will receive playback information tomorrow. And the other logistical question is, yes, can you share it with your colleagues? Absolutely, share it with everyone you know. We appreciate that. And so I have a question for you, Jeremy. What kinds of problems is semantic AI solving today, and what do you see as the next wave of AI solutions?
The problem semantic AI, I guess it's data where the problems are ones where there are complex, there's enterprise data in different places, external and internal to the enterprise, and it's in both databases, so SQL databases, and in content stores or emails, or because one side of semantics is about creating data out of text, making great data, if you like. And then the other side of semantics is about the quality of the data you've got and enriching it and harmonizing it. So that's making data great. So those are the two sides. So the sorts of projects we get involved in are, where classically you've got, let's say you've got inventory sitting in your SAP system. You've got the maintenance records sitting in a records management system. You've got your personnel sitting somewhere else. And actually what you're trying to do is you're just trying to get the right people assembled on the right vehicle with the right notes to go and maintain some piece of equipment with the right spanner. Because if you put the wrong spanner in the lorry or the submarine or the aeroplane and you get there with all the right people and you haven't got the right equipment, you've got to go all the way back, and that costs you money. And actually, although that sounds like a maintenance problem, it's not. It's actually a data problem, because you didn't have the data was not in the right place, or it couldn't be all assembled in the right way in order to prepare everything easily. So we do projects with, manufacturers' safety analytics. We work with government intelligence agencies to try and, because the data veracity is very important for them. We work with pharmaceutical and life science companies because they have a, very strong compliance and research intelligence operation. Firstly, they've got to be able to know what's going on with their products in the market, but they've also got to know how to get their products to market, high research. So it's information-intensive industries who've got a lot of text-based data. Who are using and need to extract the data out of the text, or harmonize the data together, be it internal, external, structured or unstructured.
Okay.
Does that answer the question?
I think so. So I have one that's a little bit more technical question. What is the underlying, you'll be fine. What is the underlying data model that best suits these ideas? Graph, property graph, RDF triples?
I suppose the RDF triple is important at a low level because that is a nice atomic piece of data. So for everyone who if you don't know about, there's a whole semantic set of semantic data standards in the world, W3C authorized, and the RDF triple is the atomic level of data in semantics, so subject verb object or subject predicate object. So it's an important low level format. At a high level, I think the move from relational databases to graph databases for analytics is probably one of the big changes that we're going to see in the next 5 years. We've got most of our data sitting in relational databases, and of course the issue with relational databases is you have to presuppose the question to get the answer because it's schema bound. And with graph databases, you don't have to presuppose the question. So if you're with me on that, the idea that you are schema-less is but what you've swapped is you've swapped your rows and columns in known schema for a lake of triples, which of course then needs to be brought together in a way. And the thing that brings that together are these knowledge models. But what it does is it breaks free. The business always never presupposes the question. How many people died on the way to A&E in an ambulance? Oh, I can give you the answer for that. 5 today. How many people died on the way to A&E in an ambulance when a paramedic was involved? Oh, you never asked me to capture the paramedic data, so now I'll have to go back and I'll have to put in a new schema, a new column in my data, and I'll have to extract it, transform it, and load it, and then we'll have to go back and we'll do that. That's the old way of working. Whereas with the new way, the semantic way, the graph way, you just start to capture that data going forward, and you don't have to worry about being bound by the schema. And I think that's massively important for people. So RDS at the low end, graph at the high end in terms of strategy versus implementation.
Okay. Do you have any comments?
And of course we use all of them.
We do. Do you have any comments about the best way to associate metadata with source content and how to capture the known knowns, business knowledge from the different silos in one's organization into a semantic structure?
Yes, we do. Very simplistically, I can do a webinar on that in its own right, to be honest. It's called a metadata hub, and many of our projects are about the implementation of a metadata hub that is a enterprise. So it doesn't have to start off as an enterprise. It can be a departmental enterprise hub, departmental metadata hub, which grows. But the concept is that it's one place to go for your harmonized data, metadata, and that's actually what Smartlogic's in the metadata management leadership quadrant for. Is that we do many projects to do that. So please, if you let me know who you are, we'll make sure that you get contacted.
Okay.
And it is a good idea for another webinar if you're interested. Anne.
Yes, we're always interested in more webinars.
But I haven't got time to. Yes, we know we've got methods, we've got professional skills, we've got software that does it, we've got, we can do this. This is what we do for a living.
Okay, I have one more question. Is the human burden with AI then defining and keeping metadata accurate? What other hurdles are there to getting started?
The human burden. Well, there's two sides, isn't it? ML on its own, you have to get these training sets together. And whilst that can get brushed off by, people, they are actually very difficult to assemble. Because you need a lot more. So for in this example, you need a training set for hat color, for colors. You need a training set for shirts. You need a training set for shoe size. You need a training set for hairstyle. You need a training set, and remember that there's the 3 training sets, 3 sets per data type, and actually getting them all together so that they actually work it's a big effort. What we would say is actually spend the time getting the knowledge model together. That knowledge model is a structure, semantics structure for all your business concepts and vocabulary, the concepts and the relationships. It takes less time, even though it sounds more, to get that together than it does to get the training sets together. And you then get your known knowns grounded. So that's where the energy has to go into the knowledge model. But it's done by business experts. It's not done it's not disintermediated. The knowledge model can be put together by the people who have the knowledge in their heads. That's what we spend a lot of time on, is making the thing making 7.4 easy to use, because it needs to be, someone needs to look at the knowledge and go, oh yeah, that's right. No, that's not right. But it would be right if I move that to there. And it has to be the person who understands the business subject matter.
Okay, I have another question. AI and data quality monitoring. Is this a next application?
AI and data. I don't really understand the question too much, but I'm happy to take, if you want to write in and explain a bit more, I'm happy to come back with a considered response.
Okay, I'll put that person's name down. I don't see any other questions, unless anyone's rapidly typing. I would say that is all we have. I want to thank everyone for joining us today, and look forward to having you join us for a future webinar, which there will be one in August, The Art of the Possible. So check out our website under events and and register. Thanks, Jeremy.
Thank you very much. Thank you.